Okay, so before we start class today, a couple of things to note. Homework 5 is due tonight. Homework 6 will be posted later today, and it will be due Friday of next week. So you have a good amount of time for homework 6, but homework 5 is due tonight on Gradescope. Studio 4 is also due this week. If you guys can mute yourself, I don't think everybody's muted. Thank you. All right, so Studio 4 due Wednesday, October 14th. So many of you have gotten checked off for this. Many of you have already submitted this, but for those who haven't, please use the Wednesday time to get checked off and submit before the due date. I will also upload Studio 5 sometime tomorrow. Quiz 11 is on Gradescope for you to answer, and that is due today. Exam 1 grades will be discussed on Friday, so that's our next class. Grading is on the way, and it's going well. So we'll have a quick discussion on how the distribution was for Exam 1 in the next class. Now, during the exam day, would Studio 5 will be due 2 weeks later? I'm going to look at Studio 5 and then, so it really depends on how things go with Studio 4 as well. If there is a need for it to be 2 weeks, I will make it 2 weeks. Otherwise, it'll be 1 week. It's not a very long studio. No problem. All right. So when exam 1 was going on, there was a question on Piazza regarding what happens if during finals week we have some sort of power cut or some weather related activity that goes on which is going to disrupt your internet connection. Now, with regards to that, what I want to say is that kind of event can very well happen with me. In fact, it almost did with the in the capital region. There was a storm, severe storm, which left many without power for many days. So that kind of event can happen, with anyone. But what you need to do as exam takers is try to be open with me, right? So if you are having some issue, bring that to my notice by email or WebEx Teams. Be proactive with that communication so that we can arrange for your particular situation. I would assume that most people will go through the exams without any issue. But if you are having an issue, you got to bring that to my attention so that we can work on a solution for you. So since every exam, and this is not just for this class, right? Like all the exams that you're giving are online these days, most of them at least. So that kind of situation, that kind of event is possible everywhere. So the only way to work around that is to have an open conversation about it with me. So if there is a power cut, there is a power cut. Nobody can do anything about that. Any questions or concerns before we continue with our lecture here? There have been hurricanes. Students have communicated with me. Fires in California. Students have communicated with me. So, things like that have happened, and we have worked out a solution. Okay, so it doesn't look like you guys have questions as of now. We will continue with our discussion about static hazard detection and elimination. So in the previous class, we talked about the terminology for this, to how do you identify coupled variables, coupled terms, residues, a redundant prime implicant, and then fix the static hazard problem by adding the redundant prime implicant. So we will work through this example. There's a simple example of three variables, A, B, and C. What we can do is we can fix the hazard by using the terminology, or we could also use the K-maps to fix our static hazard. So the function given to us is right at the top. Function f is A complement and B, or A and C. It's a sum of product expression, and we are going to try to first figure out whether there is a hazard that is possible, or whether there's a glitch possible or not. So first, let's do it with terminology. With three variables, you can easily tackle that with just looking at what is the residue. So let's take a look at that. So first things first, what is the coupled variable? In this particular function, both the true form and the complement form, I can see that for A. So A appears both in true form and complement form in both the product terms. So that would qualify as my coupled variable. And the terms which have A represented will be my coupled terms. So both the terms here are coupled terms. A complement and B, as well as A and C. The residue is going to be what is left over if you removed the coupled variable from those product terms. So if you remove A from the first term and if you remove A from the second term, you will be left with B, C. Those will be my residues. And then the redundant prime implicant in the case of SOP is going to be a product of the residues. So B and C. And then the hazard cover, we are essentially going to add our redundant prime implicant to fix the static hazard possibility. Now, it works out very well in the case of three variable example, but we could also look at it from the standpoint of the K-maps, and we can observe the static hazard. So what we have over here is the three variable K-map in which the ones have been entered based on the function. So for example, A complement and B, that is when A is 0 and B is 1. So that essentially maps to the vertical column of two ones over there. And then the second one is, let me use red for that, A and C, that's when A is 1 and C is 1. So that would be for, let's see, come down here, and that. The two ones that are horizontal. So that would be A and C. Once you enter all the ones and observe the blue rectangles are for the product terms that are already present in the function. Now you observe whether there is a redundant prime implicant on top of this. Clearly, when there is a change in B, when B actually goes from 1 to 0, A actually goes from 1 to 0, that's when you have the static hazard possibility, because we have not covered that with a group of two ones. And that would be our redundant prime implicant in red happens when A goes from 1 to 0. So the condition over here would be, we can actually write that condition over here as well. So input condition for accidental 0. Why accidental 0? Because it's in a sum of product form. So the condition is only one condition here. Glitch could occur when A changes from 1 to 0. It has to be from 1 to 0. Only then you will have a glitch in the SOP form. And in the same way for POS form, the change has to be from 0 to 1. Now that's about A. What about B and C? While B is 1 and C is 1. As you can see, when this is changing, for both of these, B is 1 and C is 1 for the red group. So that would be one input condition in which that glitch could occur. So that's a static hazard detection as well as elimination, right? This is the fix. Let's take a look at POS. Let me erase this from our earlier discussion. For POS, we have a product of some expression for logic function f. It is A complement or C ANDed with A or B. Now in this case, what is the coupled variable? Again, it's going to be A because A appears in complemented form here, A appears in true form over here, so our coupled variable is going to be A. What terms have A? Well, both the sum terms have A. So this guy has A and this guy has A as well. So both these terms are going to qualify as coupled terms. For the residue, we again look at the coupled terms without the coupled variable. So if I remove A from here, if I remove A complement from here, I'm left with B and C. So those will be my residues. Now in this case, the RPI is going to be a sum term because it's a POS hazard condition. So B or C, the sum of the residues. And we fix the hazard by ANDing the RPI in this case to our original function. And you can also view this from the K-map. You put in the zeros wherever the function is going to be 0. For example, if I look back at my function, A complement or C, that's when A is 1 and C is 0. Where is A 1 and C 0? That would be for this term right there. Let me highlight them slightly differently. I will use blue for this guy, and then I will map that to this one right there. So that group of two ones, that's going to be my A complement or C, and then for the second one, both A and B have to be 0, and that would be for this case right here. A and B are zeros. And then now we look for the redundant prime implicant, which is going to be the group that wraps around. So that's when, let's see, C is 0 and B is 0. A changes from 0 to 1. So A has to change from 0 to 1 here. That's the input condition, while B is 0 and C is 0. So identifying the input conditions is pretty useful. And once you identify the condition, then you can try to fix the hazard in this case. All right, questions about how to fix static hazard for both the SOP and POS case. Actually, we can write down the terminology here. So this is going to be static zero hazard, which is also called as the product of some hazard. And in this case, we get accidental 1. And in the earlier case, it would be static 1 hazard, or SOP hazard, and in this case, we get an accidental 0. So Ian says, why can't 0, 0, 0 and 1, 0, 0 be reversed? All right, so the reason for that is because the implementation of the function is in the product of some form. Now, if the implementation is in the product of some form, the change has to be from 0 to 1 for you to get an accidental 1. Because remember, one path, this path, is longer than this path. with respect to change in A reflecting at F. And because of that, and because of the fact that this is an AND gate at the end, all conditions have to be true for you to get a true at the output of an AND gate. Now, in what scenario can you get an accidental 1? Well, you can get an accidental 1 if A had changed from 0 to 1, but because it was 0 earlier, that was keeping that at 1, right? So because it was 0 here, it was probably a 1 at the output, 0 at the output. And after it changed, it took some time for that function to go back to 0, and you got an accidental 1. So the answer to your question is because of the properties of AND gates in this case. And it's a similar behavior as if you look at the previous one. Over here, because of the property of OR gate, for OR gate, what do you say? We say, okay, if any one of the conditions is true, the output is true. The only possibility for you to get an accidental 0 is when the change happens from 1 to 0. Now, this goes back actually to our first discussion. You see, when we had a simple X or X complement, in that case, we had a delay of the NOT gate that was creating that timing asymmetry. And because of that, now this is a SOP form, we were getting an accidental 0. We were not getting an accidental 1, we were only getting an accidental 0. And that accidental 0 was happening only when the input X was changing from 1 to 0. So it's and not from 0 to 1, right? When it changed from 0 to 1, it didn't matter because of the presence of OR gate. All right, so I hope that answers your question. Let's go back here. We were talking about this. All right. Now the 4 variable example for SOP, we looked at that. Actually, we did that over here in the last class. It's the same example as what's shown on the slide. There were 2 hazard possibilities here. So we added a redundant prime implicant number 1 here, and we also added a redundant prime implicant 2 over here. The fix was those 2 terms. And those 2 terms, before we fixed, we also recognized what conditions were present in order for you to get an accidental 0 or the presence of static 1 hazard. So we looked at those 2 groups and we said, all right, something is changing from 1 to 0. What is that? C is changing from 1 to 0, while D is 1, A 0, B 0. That was for the first case. And for the second case, D was changing from 1 to 0, and then A was 0, B was 1, and C was 0. So that was the second case. So for 4 variables or even for 5 variables, using the K-maps is the way to go. For 3 variables, you could simply use the terminology of coupled variable, coupled terms, and residues, and hazard cover. That's it. All right, let's go on and look at this last example. This is a 4 variable example for the product of sum hazard. The zeros have been written in the K-map based on these sum terms. So for example, let's just do one of them. Where is this? B complement or C complement? So that means B is a 1 and C is a 1. Where is B a 1 and a C a 1? That would be for all of this. And similarly, we can also do this guy. A is 1, D is 1, C is 0. So C is 0, A is 1, and D is 1. So that would be for this guy. C is 0, A is 1. Yes. And then of the last one, all of them, B, C, and D, all of them are zeros here. So that would be for this guy right there. And once you fill out the zeros, you look at where the redundant prime implicant is going to come. The redundant prime implicant is going to be, one of them is here in red, the other one is here in red. and we can actually find the sum terms for this. For the first vertical one, the top one, that is going to be A is 1, B is 0, and C is 0 as well. So that's the reason that's the reason why we have this term right here. And then for the next red one, the next RPI, we have, let's see, A is 1, B is 1, and D is 1. So that would be right here. So those two terms are going to be our redundant prime implicant in the case of the POS example. And once we AND those terms, that would fix our static zero hazard possibility. Now looking at the same example, let's try to identify the conditions. How do we state the conditions in this case? So let's start with finding the simplest SOP. What would be the simplest SOP in this case? It's the same example as before. Now, the reason why I'm doing this again is because I want to emphasize that static hazards, you can only talk about static hazards once you have fixed a particular implementation. So I cannot talk about them without talking about in what way did I implement the function. So that's why I have step number 1 over here, which is let us go for the simplest product of sum implementation, and then we can start talking about if you did one, how would you fix that problem and what are the problems in that case, right? So without step number 1, you cannot jump to step number 2. So let's start with simplest POS. So I'm focusing on the zeros. Where are the zeros? Well, let's see. A really good group is here, group of 4, and then I've got a group of this, and then I've got a group here. So those 3 things, and we have written the expressions, those are here, here, and here, are going to be our simplest product of sum. After we get this, then we are going to say, all right, if we were to implement the function using this simplest product of sum implementation, what would be the conditions in which there is a static 0 possible? Then we would start looking at redundant prime implicants. So in this case, you will have one here because you have not covered that change, and another one here. We have not covered that change. So now let's write the conditions. So let me number them here. I can number them one, maybe A. Condition A and condition B. So for condition A, what is the change? C changes. C changes from 0 to 1, while what is that? D is 1, A is 1, and B is 1. So that would be the first condition. And then the second condition would be what changes? D. D changes from 0 to 1. While the other 3 inputs are static, only one input changing. So here A is 1, B is 0, and C is 0. All right, questions about this example? So what you get over here is an accidental 1. So if C were to change from 0 to 1 while these inputs were maintained, you would get an accidental 1. All right. Now, just to summarize what we learned in this particular lecture about glitches and hazards, static 1 hazard is unexpected 0 or accidental 0, and this happens only in sum of product circuits. Static 0 hazard, which is accidental 1 or unexpected 1, that happens in product of sum circuits. Why is that the case? Because in sum of product circuits, you have an OR gate at the end, and for the OR gate, the definition of an OR gate is any one of the inputs is 1, the output is true. Which is why you get an unexpected 0 if you don't have a cover for that particular change from 1 to 0. Static 0, product of sum. Product of sum ends at the end with the AND gate. And the definition of AND gate is even if one of them is 0, if any input of the AND gate is 0, the output will be 0. So you get an unexpected 1 when the change in one of the input variables is from 0 to 1. We fix the hazard by adding the consensus terms. We also call them the redundant prime implicants. That's how we got the hazard cover. And if we were to implement a certain function, not in its simplest form, but as a set of prime implicants, as a set of all prime implicants, that is always going to be hazard free. And the reason for that is we have covered RPIs and essential prime implicants in the set of prime implicants. So if you cover redundant prime implicants in the function, then you will never have a static hazard. All right, so let us stop here with this particular lecture, and then we can continue with the next one.